since we're on the subject of having to do a problem that involves a distribution of charge, we should do this problem twice. Once to find the electric field and once to find the electric potential. Does that make sense? I think it's not unreasonable. We're going to have to do that problem anyways. So if you're ready, we'll do the electric field one first, because I think that one is one that's probably what the progress check was about. And if we're good and feel comfortable after that, because a lot of what we'll have to transfer for the electric potential question is almost the exact same stuff. So I'll start out by kind of reminding us that there's a set of steps that we're going to have to do here, but also a set of assumptions we're going to have to do. I think the first assumption we're going to make is that the electric field from any one of these pieces is always going to be directed this way away from the bar, right? Any question about, that's an important distinction, but I want to make sure we understand one of the things we have to take care of is deal with direction. And so if our bar of charge has a positive charge density, then a positive particle would be pushed away from the bar. So whether I choose this piece of the bar or this piece of the bar here, the electric field at this point will still be pushed to the left. Does that make sense to everybody? So one of the things that I think makes this problem a little easier is that every single piece of the bar contributes to an electric field that's in the same direction. The problem is every piece of the bar is a different distance away, so how much it contributes to the electric field is different for every piece. So I'd argue that this piece contributes more to the electric field because it's closer than, say, this piece does. Does that make sense? This is why we're probably going to have to break the bar up into multiple pieces and integrate. They're not going to be able to just do a simple sum or something like that. It'll have to be integrated. All good to get started? All right. So with any of these problems, remember, one of the things you have to do is you have to choose a piece of the bar that you're going to work on as kind of the generic piece that represents any piece of the bar. And so this piece I'm going to label dq, and it represents a part of the total charge of the bar. I'm going to need to consider its size and a way to point to it. So there's a couple different ways we could decide to point to it. So let me start by saying I think the easiest way to point to it would be to say that this location on the bar is 0 and that this piece of the bar is a distance x away from 0, and use x as my placeholder for where each piece is. Does that make sense? There's another way to do it, and in some circumstances, I don't know why you would want to do it this way, but you could. We could choose like the middle of the bar to be 0, and then make pieces to the left of that positive and to the right of that negative. I think that's a harder way to do it. I don't think it's necessary to do it that way, but I know that if I grab any of these textbooks and look at the different ways they've done this problem, they do it different ways each time, and there are advantages and disadvantages to each. Go ahead.
Can you also start at the point and then just have your lower bound be A, and then your upper be A plus L?
I don't see why not. That's what it's going to work out to being anyways. So, and I think that would be just fine too. So we have 3 options. I think any one of these options works great. So we could set the 0 to be here, the 0 to be here, or the 0 to be here. Anybody have a preference or care? This one? This one. Okay. So that's what we'll do. But like I said, remember, setting the 0 is kind of an arbitrary choice. And it's going to work out to be the same answer regardless of where you set 0 to be. Sometimes there are more convenient ways to set it up. I don't see any symmetrical thing here that makes setting the 0 one place better than the other. But like if you're out here, there might be reasons why you want to make 0 in the middle as opposed to the end, right? We were able to use the symmetry of one side being the same as the other side. So we don't have that here. Our next job is to kind of figure out a way of representing how much charge there is in the piece based on the size of the piece. So since I'm using x to represent where the piece is, I can say that this piece is an arbitrary small length that's going to be a little more in the x direction. And I'm going to make the assumption that I can treat the bar as if it's very, very thin compared to its length, so that I don't have to worry about how wide the bar is. Does that make sense? We're assuming it is a thin bar. And that makes sense since they gave us the charge density as a linear charge density. Now, the next part, I don't want to suffer over too much, but we want to try and write dq in charge of dx. But they already gave us lambda, and lambda is total charge over the length of the bar. That has to be equal to dq over dx. Since they didn't give us a total charge, we have to use lambda. Then I'm just going to use the lambda in the way in which it's been given to me to say that dq equals lambda dx. All good? Okay. All right, so we've taken some time to figure out that all the directions for the electric field will be in the same direction. We've taken a moment to express dq in terms of the shape of the bar. We've discussed what we think our first piece is going to be and where our last piece is going to be. So I think the next thing to do is to figure out how much each piece contributes to the electric field, and recognize that the electric field is only going to be in the x direction. All okay? Well, this is going to be equal to Coulomb's law, basically. So dq over 4 pi epsilon naught r squared in the r hat direction. Well, I think we can surmise that the r hat direction is actually now the x hat direction. And r is going to be the distance from this point to this piece. Does that make sense? So I could rewrite this as dq over 4 pi epsilon naught, and inside here, a plus x squared. All okay? All right. I need to sub in for dq now, so I have something that I can integrate. And now I just have to integrate both sides to get the total contribution to the electric field. I need to set my starting point and my ending point. My starting point is going to be 0 when x is 0. My ending point is when x is equal to L. That all okay? All right. Well, I think we're done. The next part is the calculus of it. Now we could work the calculus too, but this is probably what I would expect most of you to be able to get to on a problem like this. The calculus part of this is made a little bit harder by this decision. Not a lot harder, but a little bit harder. And the reason I say that is because if we had done what Matthias had suggested, this would just be like x squared inside there, not a plus x squared. Do you follow what I'm saying? If we had set this to be 0, then this whole distance we would have called x, and we would have set our boundary condition to be starting at a and ending at a plus L. That might appear easier to some of you. So if we do want to do it that way, this would look like the integral of lambda dx over 4 pi epsilon naught x squared, with our limits now set to be a to a plus L. We can do either one of these. There's a reason why the one on the right might be easier to do than the one on the left. So the reason is that this integration is going to be a little bit harder. You'll have to use more methods, and those methods probably aren't known to some of you. This one actually would be pretty straightforward. So I think we'll do the one on the right, because it's one I think that you guys can do with the skill set that you all have. But you'll need other skills to do this one. So let's do the one on the right. Anything that is a constant can be taken out of the integral. So we're talking about things that don't change as you go from one part of the bar to the other part of the bar. And I think we can all agree lambda doesn't change as you go from one part of the bar to the other part of the bar. And 4 pi and epsilon naught, none of them change as you go from one part of the bar to the other part of the bar. But x does change as you go from one part of the bar to the other. So that leaves us with this. Now, 1 over x squared is just x to the negative 2 power. So we can use the polynomial method to figure out what the antiderivative is. So I think we'll do that. So you add 1 to the exponent, and then you divide by the new exponent. So if I add 1 to negative 2, I get negative 1. And I'm going to divide by negative 1. So that leaves me with negative x to the negative 1 power, evaluated from a to a plus l. Now, evaluating this just means putting in the top boundary and subtracting and putting in the bottom boundary. Does that make sense? So lambda over 4 pi epsilon naught. And inside here I'll have negative 1 over a plus l minus negative 1 over a. There's not a lot left to do. I'd probably rewrite this as 1 over a minus 1 over a plus l. I will note that everything in the parentheses works out to be positive. That's good, because I would hate to find the electric field is in a different direction than we expected. So if that worked out to be negative, it would mean the electric field would be to the right and not the left, and that wouldn't make any sense. So this being positive is important. And we know it's positive because this number has to be smaller than this number. It's that simple there. I hasten to bring this up, but you can combine this if you're trying to, and I would encourage you to consider in other situations combining this into a single fraction, meaning getting common denominators and joining it all together. In this circumstance, nothing really happens. It's not particularly exciting. But there are circumstances where when you do that, you get sometimes some results that cancel out. So if you're not sure what I'm talking about, we can get common denominators on the fractions that are inside the parenthesis by just multiplying the two denominators together. And that would make this a plus l minus a. All right, we got common denominators, and then just added them together. I'm sure you've done this before. Probably a pre-calc thing, maybe even an algebra 2 thing. I don't know. It's been a long time since I was in a math class, but you've done this, right? The a minus a on top is convenient because then it gives us something that we can kind of use to get an idea for the shape of what this looks like. Like what happens if, L becomes small compared to A. We would expect that if L were small compared to A, that this would start looking more and more like a point mass, right? As L goes to 0, that is a point mass. So if you look at this, as L goes to 0, we don't get a point mass because it can't go to actual 0. But if L becomes very, 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 very small, we do start to get what looks like just a squared in the denominator. Do you guys see that? And I would expect that. I would expect it to start looking more and more like a point mass. The problem with that is because we have lambda on the top, if L becomes small, we all start having less and less charge because they gave it to us in terms of the charge density. which is why in this case, when L goes to 0, the electric field goes to 0 too, because if there's 0 bar, there's 0 charge. So that's why the L on the top is not letting us see that there's an A squared down here, but there is. There's an A squared in there, which is kind of what you would expect. Now, if lambda were actually Q over L, we would get the same. We would get the result where when L went to 0, we just have A squared on the bottom, and our charge would all be concentrated in a very small space. All right. Not a terrible example. Is that okay so far? Now, I think you should look at the electric potential, since that's what we're studying right now. And it's almost all of this same work. It's just that we have to change one thing. The electric potential for a point charge can now be used as the electric potential for a distribution of charges. We know that the electric potential for a point charge is Q over 4 pi epsilon naught times R, where R is the distance away from your point charge. All right, that is the electric potential for a point charge. Well, if you have a distribution of charges, then we just switch that to dq over 4 pi epsilon naught R. The difference is that the electric potential doesn't have any direction. So I wouldn't have to worry about the direction of the electric potential in these problems. It just adds up. Now, for this problem, there's not going to be much of a change because the direction of our electric field was all in the same direction. But for problems like where I'm looking at a point here, I wouldn't have to care about the direction of the electric field because the electric potential doesn't have direction. So all that stuff that we had to do at the beginning of the year about making sure we put the cosine or the sine in there to make sure we got just the amount that was pointed in the same direction and make sure that we were dealing with some kind of symmetrical system so that we could deal with having parts of it cancel out, none of that has to worry about with the electric potential. You just add them up. Every part contributes based on where it is instead of what direction it points. Now, like I said, we've done almost all the heavy lifting for this. We're just going to take this and apply the same rules as before, which means use our value for dq and then integrate. The integral is not going to be as comfortable for some of you because some of you don't know what we're about to do and you don't know one of the tricks we have to do here, but it's not particularly tough. So let's take a look at how this would look. The electric potential would equal lambda dx over 4 pi epsilon naught x, and we're going to integrate that from A to A plus L to get the total electric potential. It's not hardly any different than what we just did for the electric field. I'm going to pull all the same things out that I pulled out before because all of these things are constant. But I'm left with the integral of dx over x, evaluated from A to A plus L. Now, here lies the problem. We can't use the polynomial method for this. And for those of you who haven't had calculus, you've reached the limits of what you know because the only calculus you probably know is what I've taught you and how far you've gotten in AB right now, or BC. And BC probably hasn't gotten to taking the antiderivative of the inverse. And the reason we can't take the antiderivative of the inverse is if we add 1 to the exponent, we get 0. We can't divide by 0. So our rule for the polynomial breaks when we have just x to the negative 1 power. However, you're going to learn it eventually. So the antiderivative of the inverse is just the natural log. You guys have all done it now? I don't think everybody has. Today, not necessarily, but in the next couple of weeks. So we're going to use this right now because there's not that much to do after you know that that's the antiderivative. So we just sub that in. I was taught whenever dealing with the antiderivative and the natural log that you're supposed to put absolute value bars because you can't take the logarithm of a negative number. But this is a physics class, which means we deal with the physical world. If you run into a situation where what's going to be in here is going to be negative, there's probably something wrong with one of your assumptions. So you shouldn't produce a formula that's going to be acted on by numbers that can't be in your formula. Does that make sense? Like right now, we're going to be putting A and L in there. Will there be any chance that A or L would ever produce a negative number under these circumstances? That's what you're being asked to do, and that's why the absolute value bars are there. Based on what we just measured, no. A is always going to be a positive distance, and L is the length of the bar. Again, a positive distance, so there's no chance that those numbers are going to end up being negative. But you're asked to check before you do this to make sure it makes physical sense. But now that that's here, the next part is just stupid algebra. Natural log of A plus L minus the natural log of A. And I assume you remember all of your natural log rules, that when you add natural logs together, you multiply, and when you subtract natural logs, you divide. So in this case, we're subtracting natural logs, so it is always best practice to write this in the simplest manner possible. So please make sure if you are subtracting two natural logs, which is always going to happen when you're integrating, that you put it in this form.